In this video, we will discuss the last of our periodic properties, which is electron affinity. We will finish by summarizing the general trends in the three properties: atomic radius, ionization energy, and electron affinity. In our previous video, we talked about ionization energy, which is the amount of energy that is required to remove an electron from an atom. Electron affinity is sort of the opposite. That is the amount of energy that you get back from adding an electron onto a neutral atom. So the electron affinity is the energy associated with the addition of an electron to the valence shell of an atom that is in the gas phase. So again, we're starting with the neutral atom, but this time instead of having the electron as a product, we're having the electron as a reactant. So we are adding the electron to the neutral atom in the gas phase to give us the anion, the negatively charged ion, and we are releasing, in general, some energy. So the electron affinity is defined in an exothermic term. So energy is coming off, so it is the release of energy, but there are some atoms that will be endothermic, which will require an intake of energy. Some of these include alkali earth metals, as well as all of the noble gases. The noble gases are very stable, and so it is difficult to either add or remove electrons from them. The more energy that is released, the larger the electron affinity will be. And as a result, the more negative the number will be, which would correlate to a larger electron affinity. Because the electron affinity, like the ionization energy, is related to the attractive force between the electron and the nucleus that you're trying to add or remove the electron from, there is a periodic trend which follows the effective nuclear charge. So for the electron affinities, they will increase as you move across a period. So as you go from left to right, you'll notice that in general, your electron affinities will be increasing. Your halogens, those in the next to last column, will typically have the highest electron affinities. These atoms are fairly easy to get them to become anions with a -1 charge. Unlike ionization energies, however, there is no overall trend when going either up or down along the periodic table. You can see this from, for example, the oxygen column, where oxygen would have itself an electron affinity of -141, sulfur is -200, and selenium is -195. What that tells you is that it goes up and then goes back down. So there is no overarching trend vertically in your electron affinities. However, there is a strong correlation left to right, where as you go across a period from left to right, your electron affinity will increase. As a result, your fluorine is going to have the highest electron affinity of any atom. Let's now summarize our three periodic properties: the atomic radii, the first ionization energy, and the electron affinity as we move across a period of the periodic table and as we move down a group or column of the periodic table. So as we're moving down the periodic table for atomic radii, we'll notice the atoms get larger. So there is an increase in the size of the atomic radii as we move down the periodic table. And the reason for this is that as we go down, we are increasing the size of the orbitals. So we're stacking one on top of the next on top of the next. And so because we're adding an additional orbital around the previous one, they will naturally be larger. As we go from left to right, the atoms are going to get smaller. And that's because you have an increase in the effective nuclear charge. So as we go from left to right, the effective nuclear charge increases, and that will pull the valence electrons closer towards the nucleus. So atoms will get smaller as you go from left to right, and they will get bigger as you go down the periodic table. So what this means is that helium is going to be your smallest atom. First ionization energy, again, is the amount of energy that is required to remove an electron from the neutral atom in the gas phase. As we go down the periodic table, the amount of energy that's required to remove an electron decreases. It becomes easier to remove the electron. Most of the reason for this is that the outermost electrons, the ones that you are removing, are further away from the nucleus, which means they are easier to remove. You can think about it in terms of if you're trying to remove an electron, it's already most of the way out, and so pulling it that extra bit becomes easier. As we go from left to right, the first ionization energy increases. This is because the effective nuclear charge increases. So the effective nuclear charge, which is holding that electron to the atom, increases as you go to the right. So if the effective nuclear charge increases, it's holding the electron more tightly, making it harder to remove the electron. So for this reason, your highest first ionization energy will also be helium. The last one is our electron affinity, which again is the amount of energy that you get from adding an electron to a neutral atom in the gas phase. There is no definite trend in going up or down a column. However, there is a distinct trend in going from left to right. As you go from left to right across a period of the periodic table, the electron affinity decreases, becoming more negative, which means you get more energy out for adding the electron on. The reason for this is the same as the first ionization energy and the atomic radii. The effective nuclear charge. As you go across, the effective nuclear charge goes up, so there is a greater attraction of an added electron towards the nucleus.